Hello, and welcome to today's lesson on uniform distributions. Let's begin. So recall the general shapes of distributions. Today we'll be working with the uniform one, which highly resembles a rectangle. In today's experiment, we're going to look at our friend James, who's always late. Now James is going to follow a uniform distribution where he could be anywhere from 0 to 30 minutes late. Now again, like the previous lesson, it's tough to calculate exactly precisely when he'll be late, so instead we'll calculate an interval of time for James to be late. So some things about probability distributions is now going to be represented as a graph or a picture, where underneath the graph the whole area adds up to 1 or 100%, and the graph will always be positive above the x-axis. Again, related back to the idea you can't have a negative probability. So here's the one for James. So we can see some elements of it. It resembles a rectangle. And so it could be anywhere from 0 to 30 minutes late. And the area inside the rectangle has to be 100%. So all the probable times you could be late, they add up to 100% or just 1 in decimal format. Now one thing to note on this is we have a height up here of 1/30th. Now this won't always be given to us. We'd have to calculate that on our own. And we can do that by working through the area formula for rectangles. So the width of it was determined by the premise of the experiment. He's 0 to 30 minutes late, so the width is 30. And then the height was unknown, but we do know that the whole area has to equal 1. So we plug in 1 for the area, we have our unknown height to solve for, and then we have the width of our experiment. Solving for the variable h, we do get the result we see here of 1/30th for the height of this rectangle, representing the uniform distribution for James being late. So now let's try an actual problem. What's the chance that James will be between 10 and 20 minutes late? So we look at our probability distribution. We kind of have where 10's marked, here's 20, and the shaded region represents that area of chance, or that probability that he'll be between 10 and 20 minutes late. So let's run through the calculations. We need to calculate the shape and the area of this green portion. So the width is 10 units. The height, we saw earlier how to determine that, is 1/30th. So to find the area, we multiply those two together. So 10 times 1/30th gives me 10 over 30, which reduces down to 1/3 or 33 and 3 repeating. So there's a 33.3% chance that James will be between 10 to 20 minutes late. Let's try another one. Here we want to calculate what's the chance that James is at most 6 minutes late. So again, looking at the uniform distribution, we want to shade in anywhere from 0 minutes late to 6 minutes late. So the green is what we need to calculate the probability with. So the area of this rectangle, once again, grab our width. So we have 6 units is the width. The height is 1/30th. Multiplying those together, reducing down our calculation, we see that James will be late at most 6 minutes 20% of the time, or there's a 20% chance that James will be at most 6 minutes late. Now in our experiment we had everything starting at 0, but really the uniform probability distribution can start at any two bounds. So wherever the starting marker is, wherever the ending marker is, that'll determine the width. And then using the area calculation, you can find the height will basically be 1 over that width. So that way when you multiply the height and the width together, you get the requirement that the area inside your probability distribution is 1. Now here's a challenge. A machine requires maintenance at 5 years before it is completely replaced after 10 years. What is the probability that the machine will break down somewhere between 4 and 7 years of service? So I'll do this one at the end, but go ahead and think about it. Pause the video if you want to try it out. And that pretty much sums up uniform distributions. Next we'll start to look at normal distributions. So uniform are the ones where everything has an equal chance. The normal distributions are more bell-shaped or symmetric, and they are called normal distributions, where they'll be represented by something called the normal curve. Now let's go back to that challenge if you're ready. Alright, so here's our challenge. We're trying to figure out what's the probability that this machine will break down within 4 to 7 years. So we need to first represent where does that look like on the graph. So you need to mark the 4-year mark, the 7-year mark, and then kind of shade in that area that represents. This isn't a rectangle per se, but we can actually break this into two different rectangles. So we have one for the 4 to 5 year mark, and we have a second from the 5 to 7 year mark. So to calculate these areas, we just need to know some dimensions, the widths and heights of each. So the first one has a width of 1 year in this context, and the beige one has a width of 2 years. So taking the width of 1 year times the height of 0.12, that'll give us the probability for the blue rectangle represents. And we'll add to that the probability that it breaks down this 2 year region that has a 8% chance of breakdown. So putting that all together, here we have the calculation. So 1 times the 0.12 for the blue, 2 times 0.08 for the beige, adding those together. And so we see there's a 28% chance that the machine will break down somewhere between 4 and 7 years. All right, that ends our lesson for today. Thanks for watching.